Yeah, so now I want to show you how to think about the 7-sphere. Okay, so you graduated from 3-sphere school, good job. So now it's 7-sphere. And for that, I think some picture is where yeah, so this picture. So we saw this picture earlier in the movie, or something like it. So it shows a sort of circle of points down on the 2-sphere, and then the corresponding. So for each point, you get a circle up above. Those circles trace out a circle of circles. So that looks like this sort of pinkish torus, and then there's this sort of bluish one, and the two are linked. And so the observation to make is that, so just notice, this gives us another way of thinking about how the 3-sphere is built. So S3 is built by taking two solid tori and gluing them together along their boundary. That sounds crazy. So this pink solid torus and this green solid torus, if you could glue those two boundaries together, then that would make the whole 3-sphere. So how's that written? So that's written as so S1 plus D2. Right, so this is one solid torus. Like, let's see, maybe I'll draw some picture that I can point to. I guess I have a pretty good picture up there. So that's the this is me drawing a picture that's already drawn. Okay. So, all right, this is like one of the solid tori that you see there, and the point is that there's a little disk here that goes all the way around, so sort of a circle's worth of disks, and that's what you're seeing here. You have two copies of this thing, this S1 cross D2, and they're joined together along their boundary. Okay, so that's curly D for the boundary of these things. And like I said, the video sort of shows you how they're glued together along the boundary. So it turns out the same thing is true. Okay, so the same is true, same idea for the 7-sphere. So the fact is, now of course it's not an S1 cross a D2, it's an S3 cross a D4 union along the boundary with another S3 cross D4. Okay. Now, I think even that is a little hard to sort of wrap your mind around, right? So what you're supposed to imagine is this 4-dimensional disk, okay, with at every point in that 4-dimensional disk, you've got a copy of this 3-dimensional sphere, and that gives you some 7-dimensional. Like I said, I think that's hard to see, but let me just focus on the boundary here. So this boundary is just an S1 cross S1. So it's just this boundary. Here, the boundary is an S3 cross S3. So what that means is, all you really have to understand, of course, is how these two are glued together, and you can understand that by looking just at this S3 cross S3. But you just graduated from S3 school, so so all you need to do is look at the 3-sphere there and be able to imagine a little copy of the 3-sphere at every point. So I've imagined that for you. So this is supposed to be a reminder of another way the 3-sphere could look, right? There's this sort of one circle at the bottom and one circle at the top, and then all these circles in between that I'm just not drawing. It's sort of complicated. So you add a little 3-sphere everywhere around here, and do it on the other side too. It makes the picture sort of busy. So a little bit later, I'll sort of remove the rest of these and let you just see some of them. But let me tell you the sort of the key to sort of seeing these 7-dimensional manifolds. So to understand S7. We want to understand how these two copies S3 cross D4 are glued together. So that means we have to understand the boundary, which means understanding the boundary of this thing, which is S3 cross S3. And yeah, it means understanding a map from S3 cross S3 to S3. Well, to S3 cross S3. Okay, so the map sends a pair U comma V to, well, the first coordinate just remains U, but the second coordinate changes in some way, and I'll just call this C of UV. Okay, so it's just some function of U and V. And and to get S7, oh, what should I say? So I'll let C of U comma V be U times V. Okay, that's it, just multiplying. These are still quaternions. I'm just multiplying these quaternions, and that's going to be the second coordinate. And that's actually what I've drawn for you here, right? So this is the 3-sphere, and this is how it changes if you look at U at this point and multiply U times every one of these points. It just moves them around. How does it move them? Well, this circle gets sent kind of over here, and that red one gets pushed a little bit. And then as you go around, they keep on changing in some interesting way. I think I have a picture of sort of seeing how they change. So this is just zooming in on a particular fiber in the Hopf fibration, one of those circles. And and this is showing you two different possible maps. So this C that I wrote down is called C1 comma 0. And then there's another one you can write down, C2 comma minus 1 of U comma V is U squared times V times U to the minus 1. So perhaps you see a pattern here. So this is just a different map, and it gives you something that's also a 7-sphere. But these blue circles look different, and this is helping you see how they're different. So the top one, all the circles face the same direction, and if you imagine stacking them on top of each other, you get a thing that looks like this, right? So they all face the same direction, but they rotate as you go around. That's what this yellow dot is showing. This one, they don't all face the same direction. They sort of twist and turn, and if you stack them on top of each other, this is the shape that they make as they go around. So the difference between those shapes is telling you a way in which these 7 spheres are different from each other. So that's the last thing I want to say before I show you the video of the 7 spheres. This is a phenomenon that happens only in dimensions 7 and higher. Okay? So you're seeing some interesting piece of how the world works, but you can't see it in dimensions 1 or 2 or 3. And for spheres, you can't see it in dimensions 4 or 5 or 6. But you can see it in dimension 7 and in a lot of dimensions above that. So let me tell you what it is. So there are many options for the map C, H, comma, J. So I'll just say C. So for the map C that I wrote over here, this map from S3 cross S3 to itself, there are many choices of the map that you could use. And I wrote down one choice here. This produces a 7-sphere. This one also produces a 7-sphere, but of an exotic type. So this is called an exotic 7-sphere. So I'll tell you about all of the other choices and then what makes some of them exotic and others not. So there are many options for C. C, H, comma, J of UV is defined to be U to the H times V times U, let's say U, U to the H times V times U to the J. It turns out, so this is where h and j are integers. And it turns out that up to a suitable equivalence, this is all of the options. Okay? So when h is 1 and j is 0, that's the first one I told you. When h is 2 and j is minus 1, that's the second one I told you. And a fact, an amazing fact, is that if h plus j equals 1, then you get some kind of S7. Okay, so something that's roughly like S7, but it might differ in a subtle way. Okay, so it might be exotic. And I think I don't want to spend too much time talking about exotic things, except to say, well, I want to give you some idea. So I guess I have to introduce some language. So here we go. I'll use red for that to be more exciting. So homeomorphism. That's just a technical, or it's a term to say that I'm talking about a continuous map, which is a bijection, so it has an inverse, and the inverse is continuous too. So continuous inverse. But if you've been in calculus, then you know that you could be interested in having more from your functions. You could be interested in having functions that are differentiable. And there's a special name for those. Those are called diffeomorphisms. It's not just differentiable, but the derivative is differentiable, and all the derivatives are differentiable. That's called smooth. So it's a smooth map with a smooth inverse. So of course, the most useful thing I think that I can tell you now is the difference between a homeomorphism and a diffeomorphism. And that picture is also illustrating. So an example of a homeomorphism that's not a diffeomorphism is think of just one curly cube. Okay, so just a line that's just been twisted around, and then you could just pull on the ends of this line. Okay, so as you pull this, what do you get? You get a kink here, and then if you keep on pulling, then that kink just kind of flattens out. So that's a bijection. It's a map, and it has an inverse. But the problem is that, of course, doing this introduces a kink right here. So this is not in OT differentiable. So as soon as people discovered the difference between homeomorphisms and diffeomorphisms, they started saying, well, this doesn't look like a very nice thing to do. You're making this really sharp corner. Let's look for maps that avoid being diffeomorphisms. Okay? And of course, when you look at this, you say to yourself, well, that just seems abusive. There's a different way of unwrapping this wire so that you avoid kinking it. And that is a diffeomorphism. So it's a fact in this case that every homeomorphism can be replaced by a diffeomorphism. And that happens in dimension 2 and in dimension 3. But in higher dimensions, you can have examples of operations like this, homeomorphisms that are not diffeomorphisms and cannot be replaced by diffeomorphisms. So this gives you, for example, 2 different 7 spheres. But there's no way of warping this one into that one in a way which doesn't introduce some sharp corners or some non-differentiable, non-smooth structure. So that was an amazing discovery of John Milnor in 1957. Well, that's a 5. 57. Milnor proved that exotic spheres exist. And he did it by looking at what we're looking at right now. So he looked at this making a 7 sphere using this S3 cross S3. He introduced a number lambda, so lambda of h comma j. Remember I told you that if the sum is equal to 1, then you get a sphere. So let's keep that fact and define lambda to be h minus j squared minus 1. And then the theorem that he proved is that if the manifold that you get from H comma J is diffeomorphic to the usual 7 sphere, the one where H is 1 and J is 0, then lambda is congruent to 0 mod 7. Lambda is congruent to 0 mod 7. That, if you're not familiar with modular arithmetic, that just means it's a number that's divisible by 7. So 7 is good, 14 is good, 21 is good, but 15 is no good. 3 is no good, it's not divisible by 7. So, and I should say, in case you're interested, the converse to this theorem is definitely not true. And that's so maybe another story. Okay, so when you're looking at these tubes, what is this showing you? This is showing you a homeomorphism between these two spheres, which fails to be a diffeomorphism. Okay, so because you can take this, it's like a noodle, take that noodle and just straighten it out. And that would give you the noodle up above. Of course, when you do that, you have to kink the noodle. And that kinking is what makes it not a diffeomorphism. Now, for this particular noodle, you can see a different way of unwrapping it to get to the noodle above. So what's difficult, what is in fact impossible, is unwrapping the noodle not just for this one fiber, but for all the fibers in the Hopf fibration. You have to unwrap all of them at once, and it's a theorem that that's impossible. So unless I have something else, oh, that's it. So I want to now show you some video of how this works. So. So again, we're seeing S3 cross S3 here. And something I guess I should have mentioned, when you might be asking yourself, what happens when H plus J is not 1? For example, what happens when H plus J is 0? And the answer is that the manifold you get is S3 cross S4, that I've written up there. So this is sort of the boring S3 cross S4. Here, well, that's when H and J are both 0. Here, H and J are 1 and minus 1. These add up to 0, but the manifold you get is not S3 cross S4, so it's something else. But it's maybe, well, it's a good warm-up for thinking about the spheres. So there's some work in 2002 of Darwin-Crowley that completely explains every manifold that you can possibly get and how they're related and how they're not related. So think of this as just a teaser for his work. Right, this is, again, these warm-ups. So let me remind you how this is supposed to help. So you got the 3 sphere up here, and then at every point in the 3 sphere, you've got another 3 sphere, and you've got to glue that 3 sphere onto the standard one. So you've got to look at this gluing, so this transformation, and you want to see what happens to that second coordinate. So this is showing you how they twist around. So the 1 comma minus 1 has some twisting, the 2 comma minus 2 has a lot more twisting. And then I think the next thing we're going to look at is a comparison between one of these manifolds and the standard 7 sphere. That's right. One of the things you can see right away is that when these numbers add up to 1 instead of 0, then this blue line no longer passes through the boundary of the 3 ball. It gets pushed away from the boundary, so it looks like a circle here. So you're seeing that. And again, this is a close-up version circle. Notice that all those blue circles lie in the same plane as the Hopf fiber that they lie along. You can see them moving as you go. So now we're going to look at a standard sphere on the left and an exotic sphere on the right. So on the left, you're still seeing each blue circle lies in the same plane as the fiber that it's on. So thinking in terms of the tube, you would see just a straight tube that would be spinning around. Here though, well, this is the curly tube that I drew before, or I did later, and that's spinning around too. So the next thing we're going to see, so is the exotic sphere we saw first, and here's another exotic sphere. So both of these are homeomorphic to the standard 7 sphere and to each other, but neither of them is diffeomorphic to the standard 7 sphere, and they're not diffeomorphic to each other. How can you check? The subscript that I've written up there is the number lambda for these. So that one has lambda equals 3, and the other one has lambda equals 5. Those numbers are not congruent modulo 7, so they don't agree. And then, if any of you are taking Kate's topology class and learning about homology, homology is the tool that you use to prove that those are different. Okay, so this is showing you now the two, so just to sort of see how they compare. So here, the noodle's twisted up a little bit, and here the noodle's twisted up a lot more. What does that mean? So you want to visualize a homeomorphism between these, which is not a diffeomorphism. You have to visualize at every point taking this noodle and twisting it into that noodle, or maybe it's easier to think of this one and straightening it out to look more like this one. You can see for some places that looks like it might be pretty reasonable to do. Here they both look pretty straight. But then as this fiber moves around in the 3 sphere, then well, this one more or less always looks this way, and the one on that side twists up a lot more. So here's something fun. The numbers 1 and 15 are congruent modulo 7. So that means that we have the standard sphere on the left with the straight tube. But on the right, we have this 7 manifold whose invariant lambda is the same modulo 7 as the one for the standard 7 sphere. That means it doesn't distinguish them. So you can look at the picture and try to imagine, or just try to ask yourself, oh, so does that mean I can get a diffeomorphism between them? It's a homework exercise for you to think about whether or not you can do that. And then at the end here, I just wanted to give, I don't know, a more complete look at the 7 sphere. So this is the standard 7 sphere with all those little copies of S3 drawn in a lot of different places, and then the exotic 7 sphere is over on the right. And you can see a lot in there. It looks like a splitter to me. But you can see that all these blue circles always lie on each circle. They lie in that plane when the red circle is doing something else. I think I added a couple more there. The question to ask is sort of how they move, how they change as you go across different fibers. So I believe that that's more or less the end of this story, and then I have a few acknowledgments at the end here. In particular, my narrator was fantastic. The YouTube version of this has some introductory slides that you can watch and listen to this. And then, of course, I used Sage again, and I think that's great. And I think that's all that I want to tell you for tonight. So thanks.